All right, well, good afternoon, everybody. Welcome to the monthly webinar from the ACS PHYS division. I want to start by thanking the PHYS division for giving us this space and our sponsor, Phase Tech, for contributing. Today's speaker is Professor Gus Scuseria from Rice University. Gus works in electronic structure theory, and he has won a number of honors. The most recent one is the 2022 ACS Award in Theoretical Chemistry. He is a member of the International Academy of Quantum Molecular Sciences and is a fellow of ACS, APS, AAAS, Royal Society of Chemistry. And probably you all know that he, until recently, was the editor of JCPC. He has worked in many areas of electronic structure theory, from coupled cluster theory to density functional theory, from molecular quantum mechanics to solid state physics. And in the past decade or so, he has spent a lot of time thinking about strong correlation problems, which is going to be the main topic of his talk today. And so before I give him the floor for the presentation, I want to remind everybody to please write down your questions in the chat. We will collect these questions and ask them at the end. And so this is going to be how we're going to handle the Q&A session at the end. Once we're done with the general Q&A session, we're going to ask the faculty to leave, and the students and postdocs will have an opportunity to have an informal Q&A chat with Professor Scuseria. And with this, I leave the floor to Gus.
All right. Thank you very much, Marco, for that introduction. And thank you also to the division for the invitation. I'm very happy to to be here and speak about our recent work on strong correlation. The original title of the seminar was Novel Quantum Chemistry Methods for Strong Electron Correlation. But in reality, I'm going to talk about geminal theories only today. And I'll tell you in a second what geminal is all about. So here's an outline of my talk. I will introduce the concept of strong correlation, try to motivate it conceptually, what it is, why are we still dealing with it, and why traditional approaches face difficulties. I'm not going to go into the details of this. Most of it is already published, but I will, again, conceptually explain what the problem is. And then I will discuss symmetry projected states as our way of using them as a starting reference for methods where we're going to write ansatz. We're going to write wave functions that we think are good wave functions for strong correlation. Now, the main central actor of today's talk is this wave function, this ansatz called AGP, antisymmetrized geminal power. This word was invented in the 80s. It's a pretty old wave function that we have now revived, if you want. And geminal comes from the word Gemini, which means twins, which in this case is being used as a pair being two electrons fundamentally. So a geminal is a two electron wave function, and we're going to build n electron wave functions, or m if you want, n electron wave functions from pair wave functions from geminals. Models that I will present, I will benchmark them on model Hamiltonians. No results for ab initio or Hamiltonians yet. And the reason for this is because I'll show you how we can modulate, how we can turn in or turn off the interaction and have Hamiltonians that go from weakly correlated to strongly correlated by changing parameters. I will conclude with some lessons that we have learned and the future work that we're going to be doing in the next couple of years. So let me start explaining what weak correlation is, which is perhaps simpler to understand. So in quantum chemistry, we have a big advantage, which is we know exactly our Hamiltonian. It has a one-body part and a two-body part, and it's all given by kinetic energy and Coulombic interactions between electrons electrons and nuclei themselves. So the regime of weak correlation can be roughly described qualitatively or conceptually as a regime where the two-body part of the Hamiltonian is much smaller in some sense than the one-body part. So because one-body Hamiltonians can be solved exactly for fermions, electrons or fermions by Hartree-Fock theory, then if H1 is much bigger than H2, that is that we are in a pretty good situation. Now, let me clarify that the two-body part of Hamiltonian 2 can be solved exactly, okay? But the cost is combinatorial because it grows with the number of electrons, so it's practical only for small systems. Now, mean field theory, understood as taking the one-body part of the Hamiltonian and tracing the two-body part down to one body, works well under weak correlation and is qualitatively correct. Hartree-Fock is mean field theory. In this regime, where H2 is small, perturbation theory also works well. And couple cluster theory gets the right answer for the right reason at relatively low polynomial cost. So this is the weak correlation problem that we can say we have solved. Now, some people in the audience may be thinking, well, you know, CCSD parentheses T, it's 10 to the 7th, it's not cheap for me. Okay, so if you don't like then couple cluster because your molecule is way too big, you can do the FT. It's much more inexpensive. There are many functionals, I know, but it's a good alternative if you have a molecule that you need to do quantum for 200 atoms, okay? But anyway, DFT works really well for weak correlation, and couple cluster is now being called the gold standard. I like to always clarify it's the gold standard as long as you are in this weak correlation regime. So to kind of wrap this up, under weak correlation, mean field theory, Hartree-Fock theory, provides a semi-classical starting point where quantum effects are quantum. There is exchange, there is an antisymmetric wave function, but these effects can be treated by perturbation theory. Electron correlations decay quickly over space, and there is no long-range entanglement. This is key. Long-range entanglement is inexistent. Things disentangle and interact coulombically if you want, but not remain entangled. And under weak correlation, I said that the Hilbert space is combinatorially large. However, we understand that the vast majority of states in the Hilbert space are irrelevant. They are unphysical. They have very high energies. And their screening and neglect is easily dictated by the exponential couple cluster ansatz. This is essentially saying that high-rank cumulants are negligible under rapidly decaying correlations. Remember, the couple cluster ansatz is sort of a cumulant expansion of the partition function, if you want, and essentially the connected part, the excitations that are many electrons at the same time are very, very small. They can be neglected. Or if they are important, they can be approximated by lower order excitations, but products of lower order excitations, and the factorization is exponential. Okay, that's the physics. And this exponential ansatz is universal. It's good for any and every weakly correlated system. I don't need to know the details of the weak correlation. If weakly correlated, couple cluster gets it right. And this is how we deal with the combinatorial explosion of states posed by the linear Schrödinger equation. Remember, the Schrödinger equation is linear, so solving it is trivial. The problem is the cost, because the number of states blows up exponentially or combinatorially. So couple cluster is the screen error, is the ansatz that tells you what is important and what is unimportant, okay? And then from that, you solve the problem. Strong correlation is the opposite regime. I will loosely define it as H2 being much bigger than H1. And there is no good mean field theory. There is non-perturbative regime. This is a non-perturbative regime. Couple cluster and DFT fail under strong correlation. And fundamentally, the problem is that correlations do not decay spatially because electrons are entangled. And there's no universal prescription to deal with strong correlation because of the richness of the Hamiltonian itself. What I mean is that there are many different physical relevant regimes depending on these Hamiltonian parameters, magnetism, superconductivity, etc. If you are weakly correlated, it doesn't matter what your one-body Hamiltonian is, you solve it with Hartree-Fock, all right? And then you treat the rest by perturbation theory. So this strong correlation problem is truly the last frontier in electronic structure theory, and it's not an academic problem. It's very important in chemical processes, in catalysis, in photosynthesis, nitrogen fixation, molecular magnets, many, many different areas. One could say that during evolution, nature has taken advantage of strong correlation because there are processes like those that occur in this enzyme called FIMOCO, where the strong correlation is key for doing what this enzyme does, which is breaking the nitrogen-nitrogen bond. Now, as I said, strong correlation comes in many different flavors, and perhaps the simplest flavor of strong correlation is related to spontaneous symmetry breaking in mean field. This is called the symmetry dilemma because it is the case when Hartree-Fock breaks symmetry. Remember, if we have a symmetry, we have an operator, a one-body operator that commutes with a Hamiltonian. Therefore, eigenstates of Hamiltonian should be eigenstates of the symmetry operator. But what happens is that Hartree-Fock sometimes wants to break symmetry. It doesn't want to commute with a symmetry operator, and it does so to lower the energy. And it's called a symmetry dilemma because by breaking symmetry, it lowers the energy, which is good by the vibrational theorem. And this happens because Hartree-Fock is not exact. It's an approximation to the two-body Hamiltonian. But when Hartree-Fock breaks symmetry, it means that it's himself is predicting the presence of strong correlation. It breaks symmetry because of low-lying excitations that are strongly correlated with the state they're trying to describe. Now, under these circumstances, everything I said in the last few slides is not true. Couple cluster theory, when you base it on Hartree-Fock or any single determinant, and we have discussed this, many, many times in many papers. I won't repeat those here today. Now, for several years, we have been advocating to use symmetry projected states as a good reference for strong correlation. And more recently, we have focused on these electron pair models, which are technically related to U1, Lie algebra U1 symmetry projected theories. And our goal, of course, is to model strongly correlated systems accurately with polynomial computational costs. So the methods I'm going to discuss are deterministic methods, are ansatz methods. I mean, on the other hand, many people say, well, Gus, you're not going to solve this problem. It's too complicated. It's too rich, too many things. Well, so how would you do with it? Well, you run your calculation on a quantum simulator. So, this is where quantum computing comes. When things are truly entangled, maybe a quantum computer will help. I beg to differ, and I believe that there is still room to explore prescriptions, if not to deal with every strongly correlated problem, to deal with classes of them with different types of approaches. Now, for this talk, there are two classes of strong correlation that are relevant. One of them is the presence of low energy two electron excitations in the symmetry adapted restricted Hartree-Fock picture. This is sometimes what we call the pairing channel, okay? And technically, these are ladder terms if you think in terms of diagrams, in terms of Feynman diagrams. And the second type of strong correlation that I will deal with is Heisenberg-like spin-spin interactions, okay? Si vector dot Sj in the broken spin Hartree-Fock framework. Okay, so this is something that we do with broken spin orbit, broken symmetry spin orbital. This is a so-called spin channel. And if you think in terms of diagrams or couple cluster theory, this corresponds to what is called ring terms. Again, so today we will focus on AGP. It's a U1 symmetry projected state as a starting reference for strong correlation, and I will use model Hamiltonians. So the wave function that I'm going to introduce is this number projected BCS wave function, that's the AGP, and I'm going to apply it to the pairing Hamiltonian. And the other dual of this is an SZ projected generalized Hartree-Fock, total broken symmetry, spin symmetry Hartree-Fock. That wave function, we call it spin AGP, and I will apply it to two spin Hamiltonians, the XXC and the J1, J2 Heisenberg Hamiltonian. Let me clarify that AGP on the pairing channel and spin AGP on the spin channel are identical, but they are written over different subsets of orbital states, okay? These are gonna be ansatz that only deal with two states of all four possible that an orbital has. An orbital can be empty, can be doubly occupied, can have an electron up, or can have an electron down. There are 4 states. And these ansatz each deals with 2 different states. The regular AGP deals with the empty and the pair on the side, and the spin AGP deals with the up and with the down. So what is AGP? It's a seniority 0 wave function because we only deal with 2 states of the 4 possible per side per orbit. So AGP is written in terms of a pair creation operator, CI dagger up, CI dagger down. These are fermions, and that is important. We take a linear combination of these guys, and then we build a condensate over the empty state, over the vacuum, the physical vacuum. So to give you an example, if we have 4 electrons, which is 2 pairs in 4 orbitals, the AGP wave function is a superposition of all the possible later determinants, okay? Where I have 2 pairs in the states, in these orbitals, and here. There are 6 possible determinants. But the coefficient is factorized by a vector called the eta vector, which is given here. If I use the rank 2 here tensor, then this is exact because I only have 2 pairs. So it's not exact because the amplitude is factorized. So in that sense, AGP is a tensor network. It's a class of tensor networks. What is spin AGP? Well, it's the same thing, but the guy who does the pairing, if you want, is a spin flip guy. The vacuum is going to be formed by all spins downs, and then this gamma dagger is going to flip them one by one in a linear combination. That's the spin flip operator. And then we're going to form a condensate, okay, of all of these states. So again, if I have 2 up spins on 4 sides, remember my vacuum is 4 down. So I take all possible 2 flips. I have to flip 2 guys, 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. And if this coefficient were in this case, because I only have 2 up spins, where rank 2 tensor, then this will be exact. It's not a rank 2 tensor. It's a factorization from this theta vector, which is the signature of each side. So AGP puts an amplitude in every determinant of the seniority 0 excited wave function, the DOCI, not to be confused with the full CI, where we allow all 4 up, down, empty, W occupied states. This is only 2 of them. It contains a combinatorial number of determinants. I show you, I have 2 pairs in 4 sites, I have 6 states. If I have 10 pairs in 100 sites, I have a tremendous number. It's 102 states. It's a very big number. However, we can manipulate them with polynomial cost, and I will show you the principles of that. That's why we do this, because combinatorial number of states with a factorized amplitudes, however, can be manipulated with polynomial cost. It is, of course, this amplitude is factorized, is of course not exact. And if I have 10 pairs, then my tensor, my true tensor amplitude is rank 10, and AGP gives me a rank 1 decomposition. But I can build rank 2, rank 3 with correlators. So what correlators are going to do is going to start from this very simple factorization and start creating rank, tensor rank 2, 3, 4. Okay, that's what the correlators will do. What I'm saying is, I don't want the distributor projected state just to be my ansatz. It's the starting point for an ansatz where I want to come without a correlators to build tensor character. On the other hand, on the math side, AGP turns out to be an elementary symmetric polynomial, a very fascinating object or sets of polynomials that mathematicians study. And because of that, it is invariant with respect to the interchange of pairs. So it's a symmetric function when you interchange pairs. Correlators need to build non-symmetric character as needed, because as we all understand, pairs in a molecule are not symmetric. If you are in a covalent pair or you're in a lone pair, these 2 pairs are not equivalent, they're very different. So you have to build that local character of the pairs, if you want, the non-symmetric character. But the difference is that if, for whatever reason, these pairs are interchangeable because they're entangled, then this wave function has that. It lacks what is simple with Hartree-Fock, but it has the part that is very difficult to achieve with Hartree-Fock and correlators. And sometimes people, oh, that condensate is a boson. No. The algebra is fermionic, okay? It's an SU2 algebra, but it's purely fermionic. There's no error from introducing bosonization or things like that. Now, The key of AGP being an elementary symmetric polynomial is that we can compute very high rank RDMs, rank 10 if you want, with very low cost, polynomial cost, using 3 algorithms and reconstruction formula that we published a couple of years ago. And then another important aspect of this is that the AGP construction of the Hilbert space, the AGP construction base, the construction of Hilbert space based on AGP interconnects all states. It's totally different, D is missing here, from the sparse particle hole construction where only, based on determinants, where only single and double excited determinants are connected by a Hamiltonian. That's a Slater-Condon rules. Well, here, if you have 2 AGP base state and the Hamiltonian, you have a complete dense Hamiltonian. Very different representation. Now, if you start with a single Slater determinant, you have to work hard to build this long-range entanglement. This is a so-called multi-reference character or static correlation in quantum chemistry. But if you start with AGP, you have some entanglement across the board to start with. All right? It's a low rank entanglement, if you want, because it's given by a vector. So this is a low, entanglement wave function from the tensor network perspective. Now, there's one very important and intriguing case, which is when all these eta p's have the same absolute value. That case is called extreme. And it's extreme in the pairing case when the etas are the same, absolute value of 1, or when the theta's in the spin case. So this is an important case because then all the determinants have an equal weight. So it's an equally weighted wave function, a very strange beast that you would say, well, this is certainly not good for chemistry. Correct, but it's very important, for example, for superconductivity. That's a superconductor has equally weighted determinants. If you look at it from the AGP side, with just one AGP, one extreme AGP, but equally weighted determinants. And from the spin side of things, for spin systems, turns out that extreme AGP appears naturally as some sort of elected guy when frustrated spin systems cannot decide on which configuration of the many equivalent it wants to be. Extreme AGP appears naturally there as some sort of superposition of all possible cases that then give you a wave function with much lower energy than any one of them. Okay, my first example, the pairing Hamiltonian. We're going to correlate AGP. Pairing Hamiltonian is a very simple Hamiltonian where you destroy a pair, create a pair. You have this 1 energy levels. Here, NP is the number operator, P dagger is the pair creation operator. And I'm going to talk about 2 cases, 2 different flavors of coupled cluster theory. One is a traditional approach where we do linearize only CCD using the killer daggers, which is the standard approach, because if you have a Slater determinant, the de-excitations, particle hole de-excitations kill Hartree-Fock. The dagger, the Hermitian conjugate, which is a particle hole excitation, creates an excitation. So we're going to do that with the killers of AGP, which are very different from those of the Slater determinant. And then the second flavor of the theory doesn't exist for Slater determinants because it's built with this J2 operator called a Jastrow, Hilbert space Jastrow or Gatz-Wheeler correlator, which is built from number operators. Okay. So the traditional coupled cluster approach is always to use killer daggers as excitations. And these are particle holes because your reference is a determinant. But for AGP, things are different because things are non-orthogonal. And then the 2 body seniority killer, which is this guy KPQ that acting on AGP gives you 0, is written here. It depends on the etas, depends on P dagger, and N. It's just that. That's the math. And then the linearized CCD equations for AGP, you follow the standard procedure. This is the ansatz. We do AGP plus double excitations, put in an exponential, and then expand, blah, blah, blah. I'm not going to go into that. And that's the equations that you get. And then we go and solve this model. Okay, so the effective Hamiltonian is a similarly transformed Hamiltonian with this K2 correlator. And then this is truncated at the first term. That's why it's called linearized CCD. And this is what you get. Error in the energy as a function of G, the interaction strength. When G is large, this is strongly correlated. When G is close to 0, it's a one-body Hamiltonian. Hartree-Fock is exact. And GC is the critical value of G when symmetry breaks. In this case, it's number symmetry, which just happens here. So this is AGP. And then if you correlate AGP with linearized CCD, you get a pretty good answer, which is pretty much exact here, here. And this is that recoupling region, if you want, where things, there is an error. Now, CCD, the standard on Hartree-Fock, follows AGP up to some point, and then it goes straight as a line up. It just completely blows up. And the reason for that is because the pairs are condensing, and AGP is the right wave function to describe that physics. Couple cluster blows up. The other J2 couple cluster on AGP is using the exponential of this guy. This wave function is not practical for Hartree-Fock because Hartree-Fock is an eigenstate of MP and NQ. So J2 on Hartree-Fock gives you back Hartree-Fock. But AGP is not an eigenstate of J2. So e to the J2 on AGP, for example, if you have 3 pairs in 6 orbitals here, we will have 6, choose 3 combinations. I put only one of them. And then the e to the J2, all it does is creates tensor characters. So this one has 1, 2, and 3 with pairs. So you get eta 1, eta 2, eta 3. If you had 1 to 4, you get eta 1, eta 2, eta 4. But then the J2C creates this thing, e to the alpha 1, 2 plus alpha 1, 3 plus alpha 2, 3. The exponential is factorizable. So you get a factorization, not any factorization, some factorization in terms now of a rank 2 tensor, which is alpha PQ. Now, why is this important? Because it turns out that e to the J2 can convert AGP, which is a symmetric wave function, into pair mean field states, valence bond-like states, which are non-symmetric. By removing specific determinants, we do that. We make these pairs different. So for this case, an even simpler case, 2 pairs in 4 orbitals, the AGP wave function, or the AGP polynomial, if you want, is a symmetric polynomial that has all the terms, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. A pair mean field will be entangled 1 with 2 times entangled 3 with 4, which is only these 4 terms. But turns out that if you take the limit when alpha 1, 2 and alpha 3, 4 goes to minus infinity, you can check that AGP goes to pair mean field. These 2 terms get removed, okay? And then this e to the J2 AGP is also called as a resonating valence bond state because it's not your typical perfect pairing valence bond, is something a little bit more sophisticated. So we're going to do similarity transform J2 couple cluster on AGP for following the standard formula of couple cluster. But the first problem you have to deal with is that now e to the minus J2, h e to the J2 does not truncate, as in the case of couple cluster when you have particles and holes. But this exponential, this similarity transformation does not truncate, but can be resummed. We did that some years ago, and here are the results. The error per particle as a function of G over G critical again. This is G over GC equal to 0. This is the attractive side of the Hamiltonian. This is the repulsive side. I didn't have the repulsive side on the previous line. And here in red is AGP, which is roughly qualitatively correct, but in the recoupling region has a big error. J2 couple cluster goes on the other side. Okay, this is and gives a negative error as opposed to, so it's actually over correlating. And then if you do J2 couple cluster and re-optimize the eta from their mean field value, you get the blue curve, which is a better better answer. Which is just to say that in the presence of correlators, the etas that you get from mean field solution need to be changed, and that fixes a big chunk of the error. All right, so now let me switch to spin systems, and let me introduce this very simple XXZ model in 1 dimensions or 2 dimensions, which is sort of a Heisenberg-like, but not quite. It's a frustrated spin model, okay? These coefficients are fixed, but delta is a parameter. Before I tell you what delta does, let me point out that this Hamiltonian has SZ symmetry, okay? But not a square symmetry, which it has only a delta equal 1, in which case it's a Heisenberg J1 Hamiltonian, okay? And but away from delta equal 1, it's not an eigenstate. It does not commute with a square. So what the physics of this is that for delta greater than 1, nail structures, up, down, up, down, up, down in 1D, or a square checkerboard, the state is the one that is happy, that we call antiferromagnetic alignment. But the important thing is that turns out that spin AGP is the ground state in 1D and 2D when delta is equal to -1. It's a very special point, which is not, and you can think of delta also as an inhomogeneity parameter, sort of a spin orbit type screening that you are introducing in the system. And in that case, the reason we turn our attention to this Hamiltonian is because spin AGP turns out to be an eigenstate. It's a particular model Hamiltonian where spin AGP is an eigenstate. And if you keep going to the left, delta minus smaller than -1, then ferromagnetic alignment is preferred. So there are phase transitions at delta -1 and delta equal 1. Now, between -1 and 1 is critical, okay, with all the things that criticality brings from stat-mech and blah, 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 which means that the reduced density matrices decay algebraically and decay very, very slowly. Now, in the region between -1 and 1, what caught our attention is that the lowest energy AGP is a bimodal extreme distribution. So the thetas, those signatures that were etas on the pair, and I call them theta here, are +1 and -1, and they alternate signs. Okay, and this is an example of extreme AGP recognizing some sort of criticality, some sort of very strange strong correlation, and saying, okay, I got a solution for that. I get some proposal for that. Extreme AGP also picks up the staggered magnetization and picks up the phase transitions on -1 and +1 in a very simple level of theory, which Hartree-Fock cannot do at all. Now, of course, in 1D systems, the MRG, auxiliary field QMC, they do all of this correctly. Let's not say you are the only ones that can do this. But the important thing is AGP is very practical for very large systems and does not care about dimensionality, which DMRG does, and also a auxiliary field QMC. It feels it. This is a Hilbert space type of theory, and 1D, 2D, 3D just doesn't make any. I mean, obviously it's a different Hamiltonian, but the fiancet itself is not dependent on that. So what is now, we grab this spin AGP and do J2 couple cluster on top. So same as before. So we have 3 up spins on 6 sides, which is this combination of states, and AGP has a fully factorized coefficient, then e to the J2, it's adding an exponential. And if you have 1 and 2 and 3 up, you get those data. If you have 1, 2, 4, you get those data, and then the alphas between the pairs. Building rank 2 tensor on the factorized amplitudes. But again, here, it's important to point out that the exponential of J2 can convert spin AGP into dimer product states, which again are valence bond-like. But instead of being doubly occupied and occupied, here the dance is between up, down, and down, up. So it's entangling up and down spins in this dance. And by breaking some of those connections, you can go from a state which is totally symmetric, okay, to states that are like nearest neighbors, where 1 is entangled with 2, 3 with 4, and 5 with 6, and this is a product between them, or 2 with 3, 4 with 5, 6 with 1, etc. Where 1, 2, as I say, is an open shell singlet between 1 and 2. If you go to second nearest neighbors by choosing these alphas in some way, you can also describe guys like 1, 3, 2, 4, 5, 6. Here we have 2 of the open shell singlets are between second nearest neighbors, and 1 of them is between first nearest neighbor. So again, here, if you include a correlator on spin AGP, you start building entanglement, which can be geared towards near short range interactions, okay, versus very long range interactions that AGP has. AGP has all possible combinations. If you have an SZ equals 0 state and you have a whole bunch of spins, okay, and you start from all of them down, then spin AGP will flip half of them up in all possible combinatorial combinations. It's a whole thing that you treat all together with a factorized coefficient in front for each of these states, of each of these determinants, if you want. And then you do it to the J2, and now you bring the rank 2 tensor, and that's enough to start saying, okay, long range entanglement, nah, we only keep, sort of more local range. And that's how you build this nearest neighbors or second nearest neighbor dimer product states, which again, valence bond-like on the spin channel. So let's look at the some plots for the XXC model. Here is delta equal 1, the Heisenberg point. This is delta -1, where AGP, spin AGP is an eigenstate, is a ground state. And this is the agreement with the exact energy in percent. So you see here in blue is the AGP curve, and you see that it's exact at this delta -1 point, and it's very poor, well, very poor. It's not good at the delta equal 1 at the Heisenberg point. It's only 65% of the correlation energy. Why? Well, I think we all understand that a Heisenberg Hamiltonian, and even delta is greater than 1, I didn't include that part of the plot, likes antiferromagnetic ordering and likes them to be non-symmetric. It's this guy is up and this guy is down, and the next is up, and they're not the same. I mean, they cannot interchange them. And you see on that, then when you do this nearest neighbor wave function on AGP, this type of valence bond type thing, when you do just a nearest neighbor dimer mean field product wave function, you get the green, and if you add the second nearest neighbors, you get the red, which is even much better. But the important point is that e to the J2 is on AGP is here in black, and you see that that correlator is good enough, at least for this case, to create all the sort of short rangeness importance between nearest neighbors and second nearest neighbors. Again, this is actually 16 sites only. And again, this is this e to the J2 on AGP is some form of resonating valence bond that I think we are. The resonating valence bond wave function is kind of, very fussy, not very well defined. And people have used it in Monte Carlo and in other areas, and mostly stochastic methods. So I think we're the first to use these RBB states in deterministic ways that we can, our error is totally under control because we're basing it on AGP type algebra. Important thing here is that these green and red states are linear combinations of nearest neighbor products and second nearest neighbor products and combinations of them. And e to the J2 acting on spin AGP describes linear combination of dimer product states, which is actually one of the most renowned ways of the RBB wave function. Now in 2D, the situation is similar. So you see this, the reason I emphasize this is because AGP doesn't care about dimensionality. Many of the methods that work well for 1D XXC don't work well for 2D XXC, but AGP works well. This is just the error in the energy as a function of this delta parameter. 1 is a Heisenberg point. Here we go beyond, and delta -1 is that the transition, phase transition to ferromagnetic ordering, and we go all the way to the left. And AGP is in blue, and in red is J2 couple cluster, e to the J2 on AGP. And you see here for delta -1, the error goes to 0 because it's an eigenstate. And the motivation to do all of this work was precisely that, the fact that understanding that e to the J2 AGP was an eigenstate, we said, okay, so how does it do away from this point? And it does really well, but until when you get to the Heisenberg, sort of more quantum chemistry Hamiltonian with no spin orbit, okay, with no spin orbit, then it doesn't do that well. So this is why I think it's interesting. And this actually, it's the two-dimensional J1, J2 Heisenberg model on a square lattice. Here is the energy as a function of the ratio between J2 and J1. So the physics of this spin system is well known. On the right side here is where we get ferromagnetic columnar order. So we get columns or rows, if you want, rows of up spins followed by rows of down spins. So there are columns of up spins, down spins, up spins, down spins. On the left is nail order. So up, down, checkerboard type of spin configuration. In between, a freaking mess that people are still trying to figure out. But let's see what AGP does. Well, first of all, AGP here is in purple. And the first thing AGP does is it very clearly sees the phases. It declares that the lowest energy AGP is extreme, where every possible combination of which spins are up and which ones are down is equally weighted, with a phase difference between the right-hand side, okay, that columnar order, you get +1, +1, +1, +1, and then minus, plus, and the other one you get plus, minus. That's a sign of the etas or the thetas, the signature of the AGP on the side. All right, And then you say, well, what about other extreme HGPs? If extreme HGP is the lowest state, what about putting that phase on different places? And then we found 27 of them by simply demanding on this 4x4 lattice to be translationally invariant. So we can put the plus and minuses now in many different combinations. It turns out that, okay, so when you do that, then this phase transition, if you want, at 1/2, which is not correct for the exact wave function, that much we do know. I didn't say that. Here in red is, at least for this size, this is the exact energy, and you see that there is no, if there's the phase transition, well, it's more complicated. Apparently, what people may agree is that at 0.4, there's one phase transition, and 0.6, there's another one. In between, there's this famous spin liquid, and still debating about what the full structure of that thing is. I guess what I wanted to say here is that if you use a linear combination of extreme HGPs, they do nothing here on the left or nothing here on the right, because the phase is very clean. It's this phase, so you don't need the other HGPs. But as you are transitioning from one phase, columnar or row order, to the nail order, then these other guys don't lower the energy much, but it gives you a smooth curve, which is interesting. All right, so let's correlate this. The first thing we realize is that energetically of the 27, actually 3 of them are more important. So we grab those 3 extreme HGPs, okay? We take a linear combination of them and we do J2CI. I haven't talked about J2CI, but it's simply CI doubles with this operator that I showed you before, MP and Q as an excitation. In this case, it's SP plus SQ plus, okay? Remember, the guy that does the spin flips. And then you get this sort of light blue curve. If you use all 27, you get the yellow curve, which is actually pretty good. Now, when you compare that yellow curve with the red curve, you see that the error is pretty much constant. So that we call dynamic correlation. It's correlation that is constant, that we're missing, but it's independent of the interaction strength. It's independent whether you are here weakly or strong or whatever. That is sort of, the type of correlation that in quantum chemistry we know is coming from large basis set, for example. So the point is that a qualitative description of this J1, J2 Heisenberg model to describe the static correlation, it ends up requiring at least this yellow curve, which is CI doubles on 27 extreme HGPs. Okay, of course, if the lattice is bigger, 27 is going to be much bigger. I'm not going to discuss that. Now, the one thing that is very interesting is the curve just slightly below, and that curve here is J2 couple cluster on 3 of the 27 extreme HGPs. Now, why not 27? Because we haven't been able to do that calculation yet. And why is this cut here? Because it doesn't converge. See, the couple cluster equations are non-linear. CI is linear, it's variational, and you solve it, and you get a smooth curve. Couple cluster here, we're having trouble. Hopefully, we'll deal with it sometime in the future soon, and we'll be able to show you a curve. It does a little bit better than CI, and we'll see where we end up with that. All right, so I'm going to make it on time, plenty of time. So lessons that we have learned with all of this. Okay, so our approach to strong correlation advocates using symmetry projected states as reference. All right, so we think that symmetry is key. We think symmetries are crucial. When symmetries break, if you have a finite system, you must restore them. All of that we've been saying for many, many, many years. The point here, which goes back to my early slides, is that what do you do when symmetries don't break? Like number symmetry does not break spontaneously when your Hamiltonian is repulsive. It did break in the attractive parent Hamiltonian that I showed you results, and that's simply because Hamiltonian is attractive. If Hamiltonian is attractive in the two-body channel, then number symmetry can break. But if the Hamiltonian is repulsive, this is a theorem by Elliott-Leave that is not difficult to prove, number will not break. And that is sort of the crux of the electronic superconductivity, of the superconductivity of electronic origin in a Coulombic first principles ab initio type Hamiltonian. If you have phonons, okay, that's external to the electrons. The phonons create the glue that makes your Cooper pairs. That's traditional superconductivity. That's all understood, and you easily prove it by isotope doping of the replacement of your nuclei, and then you see all of the physical parameters, the critical temperature, everything changes because you change the nuclear charges. Here, and when you do cuprates or pnictides, that's not true. I mean, there is a little effect of those phonons, but because everything, it's in there, but the fundamental aspect is nobody still fully understands. There is some consensus how this electronic superconductivity appears, or superconductivity of electronic origin. All right. Now, symmetry projected states are cool because they contain a combinatorial number of determinants. Okay. So, but see, nevertheless, the reduced density matrices can be efficiently calculated to 5 rank, which is very, very handy. Now, symmetry projected states can be handled with copolynomial costs, but we have to work hard to build this amplitude tensor character. So symmetry projected states, I only talk about this U1 symmetry projected state on the spin channel, on the parent channel. It's the simplest of them. There are others. You look at our papers, we've done SU2 type symmetry projection, which includes spin and blah, blah, blah. Then the tensor network that we create is much more complex. The one with AGP is relatively simple. But in any case, you build a kind of long-range entanglement that is great for the long-range entanglement, but it's not great to describe the short-range physics like in the Heisenberg Hamiltonian. So you need to work pretty hard to build that. That is simpler to build with an exponential on a slated determinant when the slated determinant is a good mean field. But if you want to have both worlds, okay, if you want to have everything, then what we advocate here is start from something that has long-range entanglement, although very, very, very simple at its minimum character, but then from there work to build the short-range character of the wave function. So there's always conservation of misery, right? So if one way or the other things are not, and you never get a free lunch. The AGP space is globally symmetric, so that's, I'm repeating myself. So short range and decaying interactions for molecules, for example, must be constructed. If we start from a single slated determinant, then constructing invariant pair wave functions is difficult and costly, but you need to do that if you want to describe, for example, superconductivity. AGP contains its terms from the outset. And then I'm just extreme AGP, the one that every state, every determinant, if you want, is equally important, describes superconductivity of electronic origin. That was proven in the 50s by C.N. Young, very beautiful paper where he showed that if you don't allow to number symmetry to break, AGP, which BCS does, and BCS is a good mean field for traditional superconductors where phonons play a role, but if phonons don't play a role, then number doesn't break. And then what is the simplest wave function that will have Meissner effect? And C.N. Young from Young and Mills, he proved it's AGP. So this is a wave function has been around since the 60s, but hasn't been used much. And then what we have found, this is not in the literature yet, and we need to write papers because I've been talking about this for a while, but we haven't written the papers yet. For spin systems where frustration is pervasive, extreme AGP shows up saying, I am gonna be kingmaker. I'm gonna make everybody happy. And all of you guys are fighting to be the lowest energy. By the way, you're degenerate. Many of you are degenerate in chunks. You know, I'll have all of them and give you equal weight. And this has lower energy than any one of you. That's what extreme AGP does for a spin frustrated system, as I showed you for XXC in the critical region and for Heisenberg across the board. So my future work, and one final remark, this is only the beginning of the story because I only told you about either pair systems or spin systems. Real systems has both channels at the same time. The ab initio Hamiltonian is Hamiltonian, where the orbitals can have no electron, an electron up, an electron down, or a pair. Okay, so the Haber Hamiltonian is the simplest one, well, that we like and we use a lot, that is also does not preserve seniority. Okay? Seniority is the presence of only 2 states out of the 4. And to build this entity, we're using a combination of pairing and spin AGPs as starting point. And the final remark is that our models, as I told you, use symmetry projected states as reference and build correlations using exponentials of the algebra. We can also use them in the linear fashion, but but that the exponential has appeal because extensivity, to the extent that extensivity may be important in some cases, like in short-range interactions, then that will be there thanks to the exponential. And this wave function, e to the J2 acting on AGP, which is called resonating Bayes bond, in other communities like condensed matter physics, has received very little attention in physics, in chemistry, except maybe for a few. I can think of Eric Newscommon as being somebody who cares about this. Maybe Garnet Chang cares about it, but most of the community has not been yet moved away from, or has not realized yet that a single slate determinant as a reference is not going to do it for strong correlation. And with that, let me thank Guo, Tom, Tanosh, Armin, Rishabh, Shiyuan as the 6 people from the group that has, results I presented today were done by them, DOE and NSF for the funding, and thank you very much for your attention. I'm looking forward to your questions, and here are, if you want to take a look later, references to our recent papers on the subject. Thank you.
Well, thank you, Gus, for the very interesting talk. Unfortunately, it's impossible to hear the clap from people in the audience. Before we start the questions, I'm gonna remind everybody, please, to write your questions in the chat so we can read them to Professor Scuseria. If you don't mind, I'm gonna start with one question of my own, and then we can go on to the other questions. So at the beginning, you kind of differentiated strong correlation and weak correlation by looking at the relative magnitude of H1 and H2. So I was wondering what happens in a regime where they are about the same.
It's strongly correlated. Yeah, so okay. so making it bigger is the worst possible scenario. So what happens is that 1 stays 1, but 2 is many, is all. That's the many body problem. So if 1 is big, then 2, it's a perturbation. You can treat it, semi-classically with a universal recipe. But once you go to the 2-particle space, then you blow up to everything. In other words, the exponential of a 1 body on a slated determinant, it's another slated determinant. It's a Tallis transformation. The exponential of a 2-body operator blows up into the entire Hilbert space. Okay, because you start taking powers and then you just blow up. So if they are of the same, and this thing about size is just purely conceptual, right? What is the size of the Hamiltonian? What are you going to do? Take the norm of every element, blah, blah, blah. That depends on the orbital basis. It's conceptual. But for example, in the Howard Hamiltonian, where you only have 1 parameter for hopping, T, and 1 parameter for the on-site interaction, U, well, T is 1 body, U is 2 body, then T over U or U over T is a correlation string. Very clean.
Okay, Lou, do you want to go next?
Sure. We have a few questions from Rodrigo. I think I'll save my question to later. So the first question he had is, could you elaborate on why in your earlier results on paired systems, the AGP solution had a broad error, while the J2CC had comparable or even lower error, and approximately the exact solution over a broader range of G and GC?
Okay, which this is on the pairing Hamiltonian?
Yep.
Yes. Nodded. Over there. Yeah, that one.
This one. Mm-hmm. Yeah. So first of all, AGP is variational, and you see here that it's always the error is positive. Okay, but J2 couple cluster, the yellow, is not variational, and yes, in the recoupling region, see it goes on the other side. Okay. And it's overcorrelating here. When it's negative, it's overcorrelated, but it's much, much better than AGP in this region. And then when you re-optimize the ERAs, which you say, oh, okay, so my AGP, this is mean field AGP, which is the optimum ERAs. These ERAs are not extreme by any means, okay? These are all different, and the orbitals are, each one has a different occupation. When you say, well, how will these occupations change if I'm in the presence of a correlator? And then you re-optimize the eras and you get a much better result. Now, as I said, J2 couple cluster is solved by similarity transformation. It's a non-variational method. You can over-correlate, and typically, in this case, for this Hamiltonian, you go on the other side.
Okay, maybe I'll ask another question from Rodrigo, which is how would the error scale as the size of the system grows?
That's a very good one. Actually, they don't change much. That's very interesting, at least for, let me see if I have a plot here for that. Yeah, this one. This is comparing CI doubles. Can you guys see my screen well here?
Yes.
This is the same G over GC, attractive, repulsive. And here I have CI, which I didn't talk about. But see here, that's AGP. This is 50 pairs in 100 orbitals. That's a fairly large 100 electrons. I mean, this is a fairly large problem. And that's blue. And you see that both CI and linearized couple cluster do really quite well. So the error roughly is actually, if anything, gets better for larger systems than for small systems. So very little dependence on this particular case with of the error with size. And for those paying attention, there's something quite remarkable here, which is linearized couple cluster, which is extensive. That's better only in the recoupling region. Away from it, CI and couple cluster do pretty much the same. Green is a little bit better than red in this region where G over GC is 1. That's the Coulson-Fisher point, if you want. G over GC equal to 1. But for on the number pairing channel, not on the spin channel.
Okay, so we have a question from the audience, from John Montgomery. He asks, do you have an example of a chemistry problem where Hartree-Fock breaks symmetry and gives poor results, but AGP methods work well?
Those are in the literature from the 80s and when people were doing the quantum theory project, the people at the Gainesville were doing AGP and things like that. Yeah, for example, for the H2 molecule, okay, you dissociate H2 into hydrogen plus hydrogen. Hartree-Fock, restricted Hartree-Fock will break spin symmetry and be contaminated. Yeah, you get the near dissociation, you get the exact energy, the wrong wave function because it's contaminated. AGP is exact. Not even correlated, it's exact. Period. So there are many cases I can make up like that. But the truth is that the proof of all of this will be when we put together ansatz set that we can really deal with the with correlated AGP methods and the molecular Hamiltonian. That has not been done. What was done in the 80s was just AGP. Nobody has correlated AGP. And why haven't we done earlier? Because it's a learning curve and it takes an awful lot of time to be first on where nobody else has been before. This is like Star Trek, okay? We go to places, we're in a meeting, we look at each other and we say, I have no idea why it's doing this. And then it takes us weeks or months to figure that out. And then we go to the next step and we go to the next step. I mean, this wave function has given us so many surprises. We'll write papers about this in due time and tell you things like you don't expect, like all different doubles, for example, with different generators. You do CI doubles and you use different generators. You have number, you have pairs, pair hoppers, the killers, they all give the same energy, exactly the same energy if you use them all. We're not used to that. We're used to singles, doubles, triples, all give different answers. This is not what happens with AGP. So for example, there are many classes of doubles, but they're all the same. So, and so on and so forth.
There's another question from the audience, Amir Mizanjad, asking, do you see any chance for the mean field approximation in the wave function methods to be replaced with an exact approach in future instead of adding corrections to it?
You can never say never, but nah, I don't see the way that no, I don't see how we can do that. I mean, yeah, so I think the construction of these wave functions is very different from the traditional one. That's sort of a key idea here, which also opens combinations of them if you want, maybe coming from both sides at the same time. So in my view, here's this later determinant. it's a tiny little spot in the Hilbert space, and then you do singles and doubles, and then everything is orthogonal, and then it's very sparse, and then you go, you know, like what Ali Alabi does with full CI QMC type thing. So he does singles and doubles, and then starts populating, you know, vertex in the space and keeps going out and out and out. And AGP, similar projected states, everything is connected already. I mean, everything is connected. There's a metric, the space is not orthogonal. It's technically a Riemannian manifold. So the metric tells you already, you have to use a Hamiltonian in the end, but the metric already tells you what is very weakly interacting, what states are strongly interacting, and so on and so forth. So it's very different. So we haven't gotten to fully exploit these things, but I don't think they're exact solutions that one can build. Some of these Hamiltonians are integrable. So yes, Bethe ansatz gives you the exact answer. Problem with Bethe ansatz is that it gives you the ground state energy. Very difficult to get excited states. Excitation energies, yes, a few excited states. The actual wave function, no. Correlators, two-body correlators, no. So yes, they're integrable, but our approach is to have polynomial cost and ansatz. So anything you want to know about what you have calculated, you can very readily obtain.
Vanessa, I can see you have a question, but you can ask her. You can ask it yourself if you want to, or.
Sure. Just really quickly. You know, this approach is definitely going to be really important, I think, for understanding catalytic systems. And I was wondering if you thought that it would be just sort of generally applicable to catalytic systems, or if there were particular catalytic systems for which this would be.
We hope it will be generally applicable to any system, catalytic or other, where a strong correlation and multiple case, what people used to call or still like to call static multi-reference correlations are important. And you have more than 16 or 20 or 30 electrons in that active space, because then CAS-SCF plus dynamic correlation on top, none of that works anymore. We'll see if it is important. I wouldn't. I hope to be around if it's ever important, but no, seriously, you know, I'm a toolkit developer. I really not at this point worried too much about practical applications. You know, my career has been very different. You know, we work a lot on carbon nanostructures, fullerenes, and solids and band gaps, and that was all practical, very practical. If you look at my citations, they're mostly for practical stuff. And now I say, nah, you know what? I want to work on what I really care and what I think is important. And not many people have the time and the position, are in a position, you know, if you're a tenure track assistant professor, don't work on this, please. I mean, just think about another project that you are likely to have results in, you know, for 5 years. This, who knows how long it's going to take, and if it is ever going to be, you know, a paradigm changing thing. I don't know. I truly don't know.
Thank you.
We have another question.
Actually, I can read the questions. I was thinking about the SS Ephraim, the question, but curious about the correlation has significantly more pairs. Yeah, so that's in the heavy elements precisely. He's asking about how is this important for heavier elements, and that's the key. Once you go down deep the periodic table, static correlation appears in the atoms themselves. So they are nearly degenerate orbitals. And then when those orbitals go to bonding, like in metal-metal bonding, like in the famous chromium dimer or U2 uranium dimer, then there are many states are all nearly degenerate. And when you look at the excitations, for example, the optical spectrum or excitations of these systems, you see that when you talk to the experimentalists, you see that the excitations that come out are not what people expect from Lewis dot structures. So that's a way of saying this is strongly correlated. The peaks are not in the place they like them to be, and because there are collective excitations. So when you have many different sort of pairs in a very small range of energy, you're going to have them all excited at the same time. And if there are many of them, then most methods, traditional methods, will have very significant problems to deal with that.
Okay. In the interest of time, we're gonna let the we're gonna thank again Professor Scuseria. We're gonna let the faculty go, and we're gonna ask the students and postdoc to stay for an informal Q&A session. Gus?
Or everybody leaves just really quickly. I just want to